All right, so we finish with the synthesis of some cofactors, and I will use the opportunity to, as I said, to seg into some of the longevity literature that we're going to be dealing with in the last 2 lectures of the course. Folates, again, they look like this. This is where the carbon, the 1 carbon is attached. How do we make them? The organisms that make. By the way, this illustrates all the various 1 carbon transactions we've discussed already. Okay, before we say how it is made. We have seen folates, for example, in the methionine cycle. That's another methylation that's extremely important to make S-adenosyl methionine and then methylate, let's say, your DNA or something like this. We saw this here with in this lecture with pyrimidine synthesis, for example. Again, that's a source of 1 carbon units. Yeah, okay. So the way it starts, again, it starts with a purine nucleotide, and then it goes on to eventually give you folate. Okay. So the important point about folate biosynthesis is it starts with CTP. Then you have, hold on. You also have input from tryptophan biosynthesis. You have chorismate biosynthesis. Chorismate was a key intermediate in the tryptophan biosynthesis. Okay. So you get the chorismate, and that also feeds into the whole pathway. Now, folate deficiency in pregnancy is a big problem, and because it could lead to the developing fetus, the fetus will be unable for proper neural tube closure, so you have all kinds of developmental problems. And for this reason, it was because yeast is very rich in folates, and you can still find this stuff. It's called Marmite or something in Australia and England. It's supposedly tasty, and people put it on their bread. But it was given in the 20s, especially to pregnant women, to alleviate folate deficiencies and neural tube defects. Since the late 90s, folate fortified staple foods such as flour, for example, we are all taking folates if we eat enough bread or things like this, because the flour is already fortified with folate. So whenever you hear fortified blah 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 flour, it's really fortified with folate. Okay. So we don't have to have our yeast spread to take our folates. Another cofactor that's as I said, related to, I mean, as an input for its synthesis is our nucleotides is NAD, okay, which it's extremely similar. I mean, you can look at it here. That's a ribonucleotide right there, and you have, of course, the nicotinamide part up there, which is the business part of the molecule. But the whole thing looks remarkably, okay, like a nucleotide. So it's no surprise that aspects of nucleotide biosynthesis plus a few more things feed into the biosynthesis of NAD. You have nicotinamide. If you don't have the nucleotide parts, the ribo parts, you have nicotinamide, which looks like this, or nicotinic acid that is like that. So, of course, the only difference here is the amination of the nicotinamide. By the way, nicotine is also in tobacco is related to these compounds. So, how is it made in organisms that make it? You get some from tryptophan, okay? And so tryptophan biosynthesis, remember the point I was making in the last lecture, that is used not just to make tryptophan, but the intermediates are used to make, or breakdown products of tryptophan are used to make all kinds of other cofactors. NAD is one of them, and this is one input. And the other input of course, is AMP. There's the nucleotide straight up. So you combine the two, and you start seeing the molecule. Okay, that's going to be NAD. And that's all you need to remember from this point. Now, here I will diverge for a little bit and telling you how important NAD we've been talking about as an electron currency, and that's by far the most important, or the most broad use of the cofactor in the cell. But it turns out that it has some very interesting properties, and it is used by some enzymes in a different way. So these enzymes are using NAD as a cofactor, and they take the ribose part actually. So nothing to do with its electron currency properties. Okay, they use it, to acetylate various substrates, and that has very interesting downstream properties. This group of enzyme called Sirtuins. The prototype is Sir2, and you have histone HST1, HST2, HST3, a whole group. And by the way, all these Sirtuins are found from yeast in all eukaryotes, from yeast to humans. And they are thought to, for sure, to increase silencing and do all kinds of interesting things in the cell, including perhaps, if you activate them, to promote longevity. And this is the idea here, that you need NAD and the Sirtuin to extend lifespan. Okay, starting in yeast, but then the arguments were going on to other organisms as well, perhaps even humans. So the story I'm going to tell you has to do with how many of you have heard the story of Resveratrol, this compound that will activate these enzymes, the Sirtuins, and extend lifespan. This is the red wine lifespan extension story that was so big in the news, in television, radio. I mean, it was almost on a monthly basis you will hear something good about that. Well, okay, so all this story started in yeast, and it was shown by these investigators that these compounds and NAD were important for the lifespan extension of this group of enzymes. So once they work, okay, then what you're left with is the nicotinamide, okay, which was, again, remember, this is just a small part of the molecule, the business part, but it's the small part. So right up there, okay, that's the whole NAD. So it's this part. And nicotinamide can be salvaged. Okay, so this is the salvage pathway, all the way back to NAD. And here you got your tryptophan and aspartate metabolites to give you all these other intermediates and so on and so forth. So it was thought that the nicotinamide and this salvage enzyme, PNC, that takes nicotinamide back into this pathway of NAD biosynthesis, okay, is also very important and governs lifespan extension in this organism. And all right, so what's the idea? That yes, you can activate all these enzymes, okay, in the normal way, and you live longer, at least if you're a yeast. Okay, can you find artificial activators? And that's how they found resveratrol. Okay, the small molecule activator of sirtuin. So this is resveratrol is a component of. It's very common in many plants, and it's also rich in grapes, and it's found in wine. And these authors claim that if you give enough to sirtuins, they will activate them, and so you drink a lot of red wine, or you take a lot of resveratrol. Actually, if you drink a lot of wine, you will never get enough resveratrol, even by their studies, to activate the enzymes, and that has beneficial effects. And they went on and they founded a company, Sirtuins, and the company was sold to Big Pharma, GlaxoSmithKline, for almost $1 billion. That was many years ago. Okay, that was not many, maybe 10 years ago. So that was huge news. So it gives you the idea how big money and significance of these pathways. All right. Then remember, so what's the point here? That resveratrol and other activators of sirtuins, the red wine compounds, activates the sirtuins. That was the idea, okay? And that's how you live longer. Then people started publishing, that's 15 years ago, that that's not true. Actually, these things do not activate the enzymes. And to make a long story short, these authors showed very convincingly that the assay that these people had used, had used here, was flawed. It was measuring not the resveratrol part of the enzyme, but because they had to use the substrate resveratrol or the activator attached to something else, it's that something else that was doing the business of activating the enzyme, not the active ingredient that they thought they had. So people were publishing this, but nobody was paying attention because everybody was after the whole red wine, elixir or holy grail to live longer, forever, and so on and so forth. And the whole process unraveled. Okay, it is even it has been disputed. This is a super high-profile journal, Nature. It was published almost 10 years ago. That the original results were flawed, so the activators were not working. And the same authors were also saying that you overexpress or you activate, you give more Sirtuin to the cell and you will live longer. That's not even true. In all these organisms, it had no effect. Right? So the whole process unraveled. Okay, you go from the billion-dollar, miracle drug, billion-dollar company to nothing. And what happens today, or not just today, but in 2013, basically it just closed down. So it was a classic bubble hype. It rode the wave and then it went away. But that is not to say that the longevity aspects are small. Resveratrol is doing useful things. There is no question about that. But it's doing them independently of this pathway. That's the current status. Okay, so resveratrol is important, or analogs of resveratrol. They can improve the lifespan of some diseased models, especially. But whether they can extend the lifespan of a normal individual has not been shown. And more importantly, also, the way it's doing it is not through this mechanism. Okay? But we'll get back to longevity in the last two lectures of the course. So now we finished what I had to say about nucleotide biosynthesis and breakdown, and we will stop here.